Hello there, and welcome to the Sleepy Science Channel. Tonight, we drift into one of the most incredible ideas ever imagined, the invisible fabric that shapes everything we see and everything we are. Spacetime, the stage upon which every star burns, every planet turns, and every heartbeat unfolds. From the bending of light around galaxies to the slowing down of clocks, spacetime weaves the universe together in ways both elegant and strange. It curves near matter, stretches where the cosmos expands, and hums with ripples from colliding black holes. Even the air around you belongs to its vast design. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, and let the cosmos cradle your thoughts. Let's begin. Spacetime is the fabric that holds the universe together. It is not just a background stage where events unfold, but the very structure that defines how everything in the universe exists and moves. Every planet, every star, and every atom sits within it, shaping it and being shaped by it in return. It combines 3 dimensions of space with one of time into a single 4-dimensional continuum. When mass or energy is present, this continuum curves, creating what we experience as gravity. When it is empty, it remains smooth and flat. Yet even that apparent emptiness has properties capable of stretching, compressing, and transmitting waves. Without this unifying fabric, distances and durations would lose meaning, and no consistent laws of motion could exist. It is the invisible stage and the active participant, the quiet geometry that keeps the cosmos coherent from the smallest particle to the vast web of galaxies. Time and space are not separate things. For centuries, space and time were seen as distinct, one describing where things are, the other describing when things happen. Einstein's work showed that they are deeply connected, inseparable parts of a single structure. The movement of an object through space affects how it experiences time, and the passage of time can influence how distances are measured. This means that a clock carried by a moving observer will not tick at the same rate as one at rest, and rulers in motion will appear shortened to those watching. The 2 quantities blend into one system that adjusts itself to keep the laws of physics identical for everyone. Every event in the universe can only be fully described by including both its position and its moment, forming a 4-dimensional coordinate. This realization reshaped physics forever, revealing that reality is far more interconnected than our everyday experience suggests. Einstein's insight changed our understanding of reality forever. Einstein's theory of relativity redefined what it means to measure motion, distance, and time. Before his work, scientists assumed these values were absolute and universal. Einstein recognized that measurements depend on the observer's state of motion, and that all observers must agree on the speed of light. This simple principle forced everything else to adjust. Time slows for moving clocks, space contracts along the direction of motion, and simultaneity becomes relative. His insight unified mechanics, light, and gravity into one elegant picture governed by geometry rather than invisible forces. This framework has been tested for more than a century and never found wanting. From the bending of starlight to the precise timing of satellites, every experiment confirms it. Einstein's equations replaced old absolutes with relationships, showing that reality itself is dynamic, flexible, and guided by the shape of the spacetime it inhabits. Gravity is not a force, but the curvature of spacetime. What we feel as gravity is not a pull exerted through space, but the natural motion of objects following curved paths within spacetime. Massive bodies such as planets or stars distort the geometry around them, and other objects simply move along the straightest possible routes in that curved landscape. When you drop a ball, it is not being dragged downward. It is following the geometry that Earth's mass creates. The ground pushes up to stop it, creating the sensation of weight. Far above, satellites orbit by continually falling along paths that never quite reach the surface. Even light bends when passing near massive objects, following those same curves. This geometric explanation replaced the idea of gravity as a mysterious, invisible tug, revealing instead a universe where motion and structure are one continuous, elegant system shaped by mass and energy. Matey tells space-time how to curve, and space-time tells Matey how to move. This phrase, coined by physicist John Wheeler, perfectly summarizes general relativity. The presence of matter and energy determines the curvature of space-time, and that curvature dictates the motion of everything within it. The relationship is mutual and dynamic. When mass gathers, it bends the surrounding geometry, creating wells and ridges that define how particles and light travel. In turn, the motion and distribution of matter adjust those shapes continuously. This feedback loop governs orbits, tides, and the expansion of the cosmos itself. Einstein's field equations describe this interaction precisely, linking the contents of the universe to its geometry through a set of beautiful, interlocking mathematical relationships. The result is a self-consistent cosmic architecture, one in which nothing moves arbitrarily. Every path, every fall, and every orbit arises naturally from the dialogue between matter and the structure of space-time itself. Space-time can be stretched, twisted, and warped. The geometry of space-time is not fixed or rigid. It can stretch as the universe expands, twist around rotating masses, and warp near dense regions such as stars or black holes. When galaxies drift apart, it is not because they are moving through space, but because the space between them is expanding. Near a spinning black hole, the twisting of space-time drags nearby matter and light into swirling patterns, a phenomenon called frame dragging. In laboratory and astronomical observations, light from distant stars shifts and bends as it passes through varying gravitational fields, revealing the invisible contours of space-time. These distortions are measurable, predictable, and fundamental to the behavior of the cosmos. The ability of space-time to deform gives rise to everything from gravitational lensing to the slow dance of planetary orbits, proving that the universe itself is built upon a living, flexible geometry. The presence of mass slows the flow of time. Time does not pass at a uniform rate everywhere. Near massive bodies, clocks tick more slowly compared to those farther away. This effect, known as gravitational time dilation, has been measured precisely using atomic clocks on Earth and in orbit. A clock on the surface of our planet runs slightly slower than one in a satellite, which must be corrected for GPS systems to remain accurate. The reason lies in space-time curvature. The deeper an object is within a gravitational well, the slower time progresses relative to distant observers. This is not an illusion, but a measurable physical reality. Around black holes, the difference becomes extreme. To a faraway observer, objects falling toward the event horizon appear to freeze in time, while for the falling object itself, everything proceeds normally. Gravity reshapes not only motion and space, but also the very rhythm of time itself. The faster you move, the slower time passes for you. Motion itself affects time. According to special relativity, the closer an object moves to the speed of light, the slower time passes for it relative to a stationary observer. This is called time dilation, and it has been verified through countless experiments with fast-moving particles and precise atomic clocks aboard high-speed aircraft. For example, muons created in the upper atmosphere live much longer when traveling near light speed than when at rest, exactly as predicted. To the travelers themselves, nothing feels unusual. Time flows normally in their frame of reference. To outside observers, however, their clocks tick more slowly. If a spacecraft could reach near-light velocities, its passengers might experience only a few years while centuries pass back on Earth. This intertwining of motion and time means that no observer's experience of duration is universal. Every perspective is shaped by speed and relativity. Light always travels the same speed, no matter what. No matter how fast you move or which direction you travel, you will always measure the speed of light in a vacuum as exactly the same. This constancy is one of the foundations of modern physics, and the reason relativity works at all. It means that space and time must adjust themselves by stretching, contracting, or dilating to keep light speed unchanged. Experiments have confirmed this endlessly, from Michelson and Morley's interferometer tests to modern laser and particle accelerator measurements. The result is that light's behavior sets an ultimate limit on information, energy, and motion. Nothing can outrun it, and everything that moves approaches it differently depending on its energy. This universal consistency is what allows the equations of physics to hold true everywhere, ensuring that the cosmos follows the same principles from the smallest atom to the farthest galaxy. The universe would not make sense without that constant speed of light. The unchanging speed of light anchors all physical laws. Because it remains fixed, every observer in the universe can describe motion, energy, and time in a consistent way. It defines the conversion between mass and energy, dictates how information travels, and sets the structure of cause and effect. Without it, clocks and distances would lose meaning, and the fundamental equations that describe nature would collapse. The speed of light connects electromagnetism, relativity, and quantum theory into one coherent framework. It determines how fast signals can reach us from distant stars and how long we must wait to witness cosmic events. Even our definitions of the meter and the second depend on it. Light's constancy is the silent metronome of reality, a universal rhythm that unites the smallest particles with the farthest reaches of spacetime. Your GPS would fail without relativity's time corrections. Modern navigation systems depend on satellites orbiting Earth, each equipped with atomic clocks that measure time with extraordinary precision. Yet these clocks do not tick at the same rate as those on the ground. The satellites move rapidly, which causes their clocks to run slower due to special relativity. At the same time, they are farther from Earth's gravitational pull, which makes their clocks run faster according to general relativity. The combined effect results in a daily timing drift of about 38 microseconds. Though tiny, this discrepancy would create location errors of several kilometers every day if uncorrected. Engineers account for these relativistic differences so that satellite time and ground time remain synchronized. Each time your phone calculates your position, it quietly uses Einstein's theories to adjust for these distortions, proving that even everyday technology must bow to the strange curvature of spacetime. Time runs faster on a mountain than in a valley. Time itself flows at slightly different rates depending on where you are in Earth's gravitational field. A clock at the top of a mountain runs a little faster than one in a valley below. This difference, called gravitational time dilation, occurs because gravity slows the passage of time. The higher you go, the weaker the pull of gravity, and the faster time passes. The effect is incredibly small but measurable with atomic clocks. In one experiment, scientists placed two synchronized clocks a few meters apart in height and detected a measurable difference in their ticking rates. Over a human lifetime, your head ages fractionally faster than your feet. Though minuscule, these differences matter in technology and science. They confirm that gravity and time are deeply connected, and that our experience of each passing second depends subtly on where we stand within Earth's curved spacetime. The bending of light reveals the shape of spacetime. When starlight passes near a massive object, its path curves. This bending is not caused by a force tugging at the light, but by the geometry of spacetime itself. In 1919, astronomers observed this effect during a solar eclipse. They found that stars appeared slightly displaced from their usual positions as their light passed close to the sun. The measurements matched Einstein's predictions exactly and provided one of the first confirmations of general relativity. Today, scientists use this bending of light to study the invisible structure of the universe. By observing how light from distant galaxies is deflected by clusters of matter, astronomers can map regions filled with dark matter that emit no light at all. Every distorted image we see in deep space is a direct imprint of spacetime's curvature, revealing that gravity shapes not just motion, but the very path of light itself. Gravitational lensing turns space into a cosmic magnifying glass. When light from a distant galaxy passes near a massive object, such as a cluster of galaxies, the gravity of that cluster bends and focuses the light. The result is an effect known as gravitational lensing. Depending on the alignment, it can produce arcs, rings, or even multiple images of the same background object. This natural magnification allows astronomers to study galaxies that would otherwise be too faint or too far away to detect. It also reveals the distribution of dark matter, which makes up most of the mass in the lensing cluster. Scientists can analyze how the light is distorted to reconstruct a detailed map of the invisible structures shaping the cosmos. Gravitational lensing is one of the most powerful tools in modern astronomy, transforming space-time itself into a vast telescope that magnifies the universe's most hidden and distant realms. Black holes are regions where space-time collapses. When a massive star exhausts its nuclear fuel, gravity can crush its core to an extreme density, creating a black hole. In this state, the curvature of space-time becomes so intense that not even light can escape. The region's boundary, called the event horizon, marks the limit of visibility. Beyond it, gravity dominates so completely that space and time lose their usual meaning. At the center lies a singularity, a point where density and curvature become infinite and our known laws of physics break down. To a distant observer, an object falling toward a black hole appears to slow and fade, never quite crossing the horizon. To the object itself, time flows normally as it plunges inward. Black holes are not holes in space, but regions where space-time itself has collapsed into a state of pure gravitational geometry. The edge of a black hole is called the event horizon. The event horizon surrounds every black hole and marks the point at which escape becomes impossible. It is not a solid surface, but a boundary in space-time where gravity's pull equals the speed of light. Anything that crosses it, whether matter or radiation, is trapped forever. To an outside observer, objects falling toward the horizon appear to slow down, dim, and freeze in time. From the falling object's perspective, it passes smoothly through without noticing anything unusual. Quantum theory predicts that faint radiation escapes from just above this region, known as Hawking radiation, which causes black holes to slowly lose mass. The event horizon represents the meeting point of relativity and quantum mechanics, where our current understanding begins to fail. It is the cosmic boundary between what can be known and what will remain hidden inside the darkness forever. Inside a black hole, space and time switch roles. Within a black hole, the curvature of space-time becomes so extreme that the usual distinction between space and time breaks down. Crossing the event horizon changes the rules of motion completely. Once inside, moving forward in time means moving inevitably toward the singularity at the center. There is no path that leads away from it, because every possible direction points inward. To an outside observer, anything falling in appears to freeze at the edge, but to the falling object, the descent continues normally. This reversal shows that time and space are not fixed categories but flexible aspects of geometry shaped by gravity. The singularity itself is not just a point in space, but a moment in time that everything inside must eventually reach. Inside a black hole, physics as we know it collapses into mystery. Space-time can ripple like a pond. Massive bodies such as black holes or neutron stars can disturb space-time so violently that ripples spread outward at the speed of light. These ripples are called gravitational waves. Einstein predicted their existence in 1916, but they remained undetected for nearly a century because their effects are so small. The passing gravitational wave changes the distance between objects by less than the width of a proton. In 2015, scientists finally detected them using instruments sensitive enough to measure these minute distortions. The signal came from two black holes colliding over 1 billion light-years away. Gravitational waves allow us to observe cosmic events that emit no light at all. They prove that space-time is not a static backdrop, but an elastic fabric that vibrates, carrying the stories of distant cataclysms across the universe like ripples on a vast cosmic ocean. Those ripples are what we call gravitational waves. Gravitational waves are distortions that travel through space-time whenever massive bodies move or collide. They are not sound or light, but ripples in the geometry of the universe itself. As they pass through Earth, they stretch and compress space by tiny amounts, detectable only with the most sensitive instruments. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first detection in 2015. The signal came from two black holes merging, confirming a century-old prediction. These waves have opened an entirely new field of astronomy that listens instead of looks. By studying their shapes and frequencies, scientists can determine the masses, distances, and spins of their sources. Gravitational waves reveal events hidden from all telescopes, such as black hole collisions and neutron star mergers, giving us a way to observe the universe through the motion of space-time itself. We have detected gravitational waves from colliding black holes. When two black holes orbit each other, they lose energy by sending out gravitational waves. As they draw closer, the waves grow stronger and more frequent until the black holes finally merge in a burst of gravitational energy. In 2015, scientists detected the first of these signals after it traveled more than 1 billion light-years to reach Earth. The data revealed two black holes spiraling together before forming a single, larger one. This event released more energy in a fraction of a second than all the stars in the observable universe combined. Each new detection since then provides unique information about the masses, spins, and distances of these cosmic giants. Listening to gravitational waves allows astronomers to study the universe through gravity itself, unlocking an entirely new way to explore events too dark to see directly. Every collision sends tremors through the fabric of the cosmos. When two massive bodies collide, space-time responds with ripples that radiate outward forever. These gravitational waves move at the speed of light, stretching and compressing space as they pass. Even now, faint echoes of ancient collisions are moving through you, changing the distance between atoms by less than a fraction of a proton. Instruments such as LIGO and Virgo can detect these minuscule tremors, allowing scientists to reconstruct the cosmic events that created them. Each signal is a fingerprint of a distant cataclysm, such as black holes merging or neutron stars smashing together. These observations confirm that the universe is dynamic and alive. filled with constant motion and energy. The cosmos is not silent, but filled with the quiet music of gravity, a rhythm of ripples spreading endlessly through the boundless ocean of spacetime. Time dilation has been measured in airplanes. Einstein's prediction that moving clocks tick more slowly than stationary ones has been tested directly. In the 1970s, scientists placed atomic clocks aboard commercial airplanes and flew them around the world, while identical clocks remained on the ground. When compared, the flying clocks showed slight differences in elapsed time, precisely matching Einstein's equations. Both motion and altitude contributed to the effect. Higher speed caused time to slow, while weaker gravity at altitude made time run faster. The combined result matched the predictions perfectly. This experiment confirmed that relativity governs the passage of time not only near black holes or stars, but also in everyday circumstances. Modern technology, from satellites to navigation systems, depends on these corrections. Every journey by air quietly demonstrates that time is flexible, flowing differently depending on speed and gravity's influence. Even your head ages faster than your feet. Gravitational time dilation affects you every second of your life. Because your head is slightly farther from Earth's center than your feet, it experiences a weaker gravitational pull, meaning time runs faster there. The difference is tiny, only a few billionths of a second over a lifetime, but it has been measured precisely using atomic clocks placed at different heights. In experiments, scientists have confirmed that even a height difference of a few centimeters can alter how quickly time passes. This discovery demonstrates that gravity influences time everywhere, not just near massive stars or black holes. It also means that time is not uniform across the planet, or even within a single body. You live within a gentle gradient of time, where each heartbeat occurs in a slightly different moment than the one before, sculpted subtly by Earth's gravity. Spacetime is four-dimensional, but we perceive only three. The universe contains three dimensions of space, which we know as length, width, and height, and a fourth dimension called time. Together, these form a unified structure known as spacetime. We experience the spatial dimensions freely, moving in all directions, while time seems to flow in one. Physics, however, shows that space and time are part of the same continuum. Every event has both a location and a moment, inseparable from one another. Two observers moving differently through space will disagree about the passage of time, yet both will describe the same reality. Relativity unites the four dimensions under one consistent geometry, explaining motion, gravity, and causality. Although we cannot visualize four dimensions directly, mathematics reveals their harmony. The universe is not divided into space and time, but woven together into one seamless, dynamic whole. The fourth dimension is time itself. When we speak of the fourth dimension, we are not describing an unseen direction in space, but time itself. Every event in the universe occurs at a specific place and a specific moment, requiring four coordinates to define completely. This view transforms our understanding of motion. Movement through space is also movement through time, because both are parts of the same framework. Observers in different states of motion will slice this four-dimensional reality differently, experiencing distinct versions of what they call now. Thinking of time as a dimension helps explain why simultaneity is relative and why cause and effect remain consistent even when measurements vary. The fourth dimension is not mystical or abstract. It is an integral component of the geometry that binds the cosmos, connecting every point in space to every instant in history through the continuous structure of Kamau. Spacetime. The universe may contain extra dimensions beyond the four we know. Some advanced theories in physics suggest that the familiar four dimensions might not be the entire picture. Ideas such as string theory and in theory propose that additional dimensions exist, hidden from our perception because they are compact and curled up at unimaginably small scales. These extra dimensions could explain why gravity is weaker than the other fundamental forces and how all the forces of nature might unify under one framework. Although we cannot observe these dimensions directly, their effects might appear in subtle gravitational measurements or high-energy particle collisions. Experiments continue to search for signs of these hidden layers of reality. If they are ever discovered, our understanding of the universe will expand dramatically, revealing that the space we move through every day may be only a small part of a much richer and more complex cosmic geometry. Tiny hidden dimensions could be curled up at subatomic scales. According to string theory, additional dimensions might exist everywhere around us, folded so tightly that they are smaller than atoms. These curled-up dimensions would determine the properties of particles, such as mass and charge, through the way they are shaped. Imagine a straw viewed from far away. It appears as a simple line, but up close, it has circular depth. Extra dimensions could behave similarly, invisible at human scales, but vital to the universe's structure. They would exist at the Planck length, the smallest measurable scale, influencing how particles interact and how forces combine. Although these dimensions cannot be seen directly, physicists are searching for indirect evidence in particle accelerators and gravitational experiments. Discovering them would transform our understanding of reality, showing that space itself hides intricate patterns smaller and more fundamental than anything we have yet observed. String theory suggests there may be 10 or 11 dimensions. String theory proposes that the basic building blocks of reality are tiny vibrating strings rather than point-like particles. Each vibration corresponds to a specific particle or force. For the mathematics of this theory to be consistent, spacetime must contain more than 4 dimensions, usually 10 or 11 depending on the version. The extra dimensions are thought to be compact and invisible at human scales, curled up so tightly that we cannot perceive them directly. These hidden dimensions allow the theory to unify all known forces, including gravity, into one coherent framework. Though experimental confirmation remains elusive, string theory has provided profound insights into black holes, quantum gravity, and the structure of the universe. It suggests that our visible world is only a small portion of a far greater dimensional reality waiting to be understood. If you could see all dimensions, reality would look entirely different. Our senses are limited to perceiving 3 dimensions of space, so we experience the world through surfaces, edges, and volumes. If we could perceive higher dimensions, everything would appear transformed. Objects that seem separate might be connected, and events that appear sequential might unfold together. In a higher dimensional perspective, distance and isolation could lose meaning. Mathematics allows us to imagine these realms, where geometry is richer and more complex than we can visualize. Some theories suggest that these dimensions influence the universe's fundamental properties, from particle behavior to cosmic structure. If we could see all dimensions, we might perceive entire timelines at once and understand connections that now seem hidden. Higher dimensions challenge our understanding of existence itself, suggesting that the world we know may be only a narrow slice of a much deeper and more intricate reality. The Big Bang created both space and time together. The universe did not begin within space. Space itself began with the Big Bang. At that moment, the cosmos expanded from an incredibly hot and dense state, giving birth to both space and time simultaneously. There was no before this event because time itself had not yet begun. As the universe expanded, matter and energy cooled and spread, eventually forming stars, galaxies, and planets. The faint afterglow of this event, known as the cosmic microwave background, still fills the sky today. Modern cosmology shows that space-time is not a static container, but a dynamic entity that evolves with the universe. Asking what happened before the Big Bang is like asking what lies north of the North Pole. The concept no longer applies. The beginning of space-time marks the true origin of everything, the first moment from which all moments flow. There was no before the Big Bang. The Big Bang was not an explosion that happened in space. It was the creation of space and time themselves. Before it occurred, there was no before, because time had not yet begun. The laws of physics, as we understand them, break down when traced back to that singular moment. Asking what came before the Big Bang is like asking what lies north of the North Pole. The question has no meaning within the framework of our universe. Time began as the universe expanded from a state of infinite density and temperature into the vast cosmos we see today. Every second, every atom, and every star came from that first unfolding. In the earliest moments, space and time were intertwined, forming the foundation on which all structure would later rise. The Big Bang marks not only the beginning of matter, but the beginning of existence itself. The universe has no center because space is expanding everywhere. When we look out into the universe, galaxies appear to move away from us in every direction. It might seem as if Earth is at the center of a cosmic explosion, but that is an illusion. The expansion of the universe is not an explosion into empty space. It is the stretching of space itself. Every point in the cosmos sees the same pattern of recession because the expansion happens everywhere at once. There is no central location where the Big Bang occurred. Instead, the entire universe was once contained in an extremely dense state that expanded uniformly. No matter where you stand, distant galaxies appear to recede, and the farther away they are, the faster they move. This universal symmetry means the cosmos has no privileged center. The expansion of space is an equal, ongoing process that defines the geometry of reality itself. Galaxies drift apart as space-time itself expands. Galaxies are not flying through pre-existing space like debris from an explosion. Instead, the space between them is stretching. The galaxies themselves remain relatively still, held together by their own gravity, while the fabric of space-time expands around them. As it stretches, the wavelengths of light traveling through it also lengthen, causing the redshift astronomers observe in distant galaxies. This redshift is direct evidence of the universe's ongoing expansion. Over billions of years, this stretching has carried galaxies farther and farther apart, turning the once dense, burly cosmos into the vast, thinly populated universe we see today. Even the light from distant stars is being pulled to longer wavelengths as the space it travels through continues to grow. The expansion of space-time is not just a movement, but an intrinsic change in the very geometry that defines distances and motion throughout the universe. Expansion does not mean things move through space, but that space itself grows. A common misconception is that galaxies are speeding through space away from one another. In reality, they are mostly stationary relative to their local regions, and it is space itself that is expanding. To visualize this, imagine dots drawn on a balloon. As the balloon inflates, the dots move apart, not because they are moving on the surface, but because the surface itself stretches. In the same way, the universe expands by creating more space between galaxies, without any need for motion through an external void. There is no edge or center to this growth. It happens uniformly everywhere. As the scale of the universe increases, the light traveling across it also stretches, giving us clues about how fast the expansion occurs. This understanding transforms the concept of motion itself, revealing that the universe's growth is the growth of space-time rather than the movement of matter within it. the expansion of space-time is accelerating. For much of cosmic history, scientists believed that gravity would gradually slow the universe's expansion. Then, in the late 20th century, astronomers discovered something unexpected. Distant supernovae were dimmer than predicted, indicating that the expansion was not slowing down, but speeding up. The universe is stretching faster with time. This acceleration implies that some unknown form of energy, acting against gravity, fills all of space. The discovery transformed cosmology, forcing scientists to rethink the long-term fate of everything. As space-time expands faster and faster, distant galaxies will eventually recede beyond our observable horizon, vanishing from view forever. The acceleration means that the universe's growth is not a simple continuation of the Big Bang's momentum, but a new phase driven by something mysterious and pervasive. The expansion of space-time is not only ongoing but increasing, reshaping the cosmos on the largest possible scales. Dark energy may be driving that acceleration. To explain why the expansion of the universe is accelerating, scientists introduced the concept of dark energy, a mysterious form of energy that fills all of space evenly. Unlike gravity, which pulls things together, dark energy exerts a repulsive effect that pushes galaxies apart. It currently makes up about 70% of the total energy content of the universe. No one knows what dark energy truly is, but it may be related to the cosmological constant that Einstein once proposed and later dismissed. Its effects can be measured through observations of supernova, the cosmic microwave background, and the large-scale structure of galaxies. If dark energy remains constant, the universe will continue to accelerate indefinitely, growing colder and emptier over time. Understanding dark energy is one of the greatest challenges in modern physics, holding the key to the ultimate fate of space-time itself. We do not yet know what dark energy truly is. Dark energy is one of the most profound mysteries in all of science. It accounts for most of the energy in the universe, yet we cannot detect it directly or explain its nature. It does not emit light, interact with matter, or cluster like normal energy. It simply accelerates the expansion of space-time. Some theories suggest it could be a property of space itself, a constant energy density that emerges from quantum fields. Others propose that it might vary over time, or that our understanding of gravity is incomplete. Despite decades of observation, every measurement confirms only its effect, not its essence. Whatever dark energy is, it determines the long-term evolution of the cosmos. Whether the universe expands forever or meets a different fate depends entirely on this invisible influence that fills the void, yet defines the structure of everything within it. The universe's geometry depends on its density. The overall shape of the universe is determined by how much matter and energy it contains. If the total density is high enough, gravity can curve space-time inward, creating a closed geometry similar to the surface of a sphere. If the density is too low, space-time curves outward, producing an open, saddle-like shape. A perfectly balanced density yields a flat universe, where parallel lines remain parallel forever. Astronomers study the cosmic microwave background radiation to measure this curvature, using subtle patterns in the light to infer the geometry of space-time. So far, the evidence suggests that the universe is very close to flat, with only a tiny margin of error. The relationship between density and curvature reveals how matter, energy, and geometry are inseparably connected. The universe's shape is not imposed from outside, but sculpted from within by its own contents. A flat universe means space-time has perfect balance. A flat universe is one in which the geometry of space-time follows the familiar rules of Euclidean space. Parallel lines never meet, triangles have angles that add up to 180 degrees, and large-scale curvature is effectively zero. Achieving this balance requires a precise relationship between matter, energy, and expansion rate. If there was slightly more mass, the universe would eventually collapse slightly less, and it would expand too quickly for galaxies to form. The fact that it is so finely balanced puzzles cosmologists, who call it the flatness problem. The leading explanation is cosmic inflation, a brief but intense burst of expansion in the early universe that smoothed out any initial curvature. The result is a cosmos that appears geometrically perfect, a delicate equilibrium that continues to define the structure and destiny of everything within it. Curved spacetime could loop back on itself. If spacetime is curved enough, it could wrap around, allowing a traveler moving in one direction to eventually return to their starting point without ever turning around. This concept applies to a closed universe, where the geometry of space resembles the surface of a higher dimensional sphere. In such a universe, there would be no boundaries or edges, yet space would be finite. You could, in theory, keep going straight and eventually arrive where you began, though the scale of such a journey would be unimaginably vast. Observations so far suggest that the universe is nearly flat, but tiny deviations could reveal subtle curvature. If the cosmos does curve back on itself, it would mean that the universe is self-contained, a structure with no outside and no end, where space and time form an endless loop of cosmic continuity. A closed universe might eventually collapse in a big crunch. If the density of matter and energy in the universe were high enough, gravity could eventually overcome the expansion and pull everything back together. In such a scenario, galaxies would slow their outward drift, reverse course, and move closer until the entire cosmos collapsed in a final, fiery contraction. This hypothetical event is known as the Big Crunch. The universe would end as it began, in an extremely dense and hot state. Some theories suggest that such a collapse might be followed by a new expansion, forming a cycle of births and deaths. Although current observations indicate that the expansion is accelerating rather than slowing, the possibility of a closed, recollapsing universe remains a fascinating idea. The Big Crunch reminds us that space-time itself is dynamic, capable of both unfolding and folding back into the singular state from which it first emerged. An open universe could expand forever. If the universe does not contain enough matter and energy to halt its expansion, it will continue to grow indefinitely. In this open universe scenario, galaxies will drift farther apart until the night sky becomes dark and empty. Stars will exhaust their fuel, black holes will slowly evaporate, and all remaining matter will decay into faint radiation. Over unimaginable timescales, even light will stretch to wavelengths too long to detect, leaving a cold, featureless void. This future, sometimes called the heat death of the universe, represents a state of maximum entropy, where energy is evenly distributed, and no work can be done. Although it sounds bleak, this fate is consistent with current observations showing that expansion is accelerating. An open universe expanding forever demonstrates that space-time is not eternal in form, but ever-changing, shaped by the delicate balance of its own contents. The shape of space-time determines the fate of everything. The geometry of the universe is more than an abstract concept. It dictates how everything within it evolves. Whether the cosmos is open, closed, or flat determines whether it will expand forever, collapse, or hover in balance. The shape of space-time affects how light travels, how galaxies form, and even how time unfolds. Small variations in density in the early universe caused local curvatures that became the seeds of stars and clusters. The large-scale curvature influences the global destiny of everything. In this way, geometry becomes destiny. Space and time are not passive backgrounds, but active participants in cosmic evolution. The curvature of spacetime, sculpted by matter and energy, is the ultimate architect of the universe's story, from the formation of the first atoms to the possible fates that lie billions of years ahead. Even empty space has structure. At first glance, a perfect vacuum might seem truly empty. Yet modern physics reveals that even regions without matter or radiation possess properties and energy. Space is filled with quantum fields that fluctuate constantly, creating fleeting disturbances that give rise to virtual particles. These fluctuations contribute to a background energy that pervades the universe. They also affect the behavior of matter and light, influencing how particles interact and how forces operate. The so-called vacuum is not void, but a dynamic, restless sea at the foundation of reality. Even the expansion of the universe may be linked to this energy. What appears empty is, in truth, an intricate landscape of potential and activity. Space, far from being nothingness, is a living field whose invisible structure supports and shapes everything that exists within it. Quantum fluctuations stir the vacuum of spacetime. Even in the absence of matter and light, the quantum vacuum seethes with activity. Tiny fluctuations in energy continually occur due to the uncertainty principle, which forbids absolute stillness. These fluctuations briefly create pairs of virtual particles that appear and vanish almost instantly, borrowing energy from the vacuum before returning it. Though they exist for only fractions of a second, their effects are measurable. They slightly alter the behavior of electrons, shift energy levels in atoms, and even influence how forces behave. In the early universe, such fluctuations may have seeded the first tiny variations in density that later grew into galaxies. The vacuum is not empty but alive with quantum motion, a foundation that blurs the line between existence and nothingness. Spacetime, at its deepest level, is a restless field where creation and annihilation happen continuously and invisibly. Space is never truly empty. Even in the vast regions between galaxies, space contains more than meets the eye. It is filled with faint radiation, ghostly particles, and fluctuating quantum fields. The energy of these fields means that no part of the universe is entirely devoid of activity. This ever-present background influences the behavior of particles and shapes how the cosmos evolves. Light traveling through intergalactic space is affected by these subtle interactions, while gravity responds to the energy they hold. On the smallest scales, the vacuum is alive with movement. On the largest, it helps drive cosmic expansion. What appears to be emptiness is actually the most fundamental state of matter and energy, a baseline hum from which all physical processes arise. In truth, the quietest parts of the universe are never still, but gently vibrating with the hidden dynamics of space-time itself. Virtual particles flicker in and out of existence constantly. In quantum physics, empty space is a theater of continuous creation and destruction. Virtual particles emerge briefly, interact, and then vanish, leaving behind subtle traces of their presence. They are not directly observable, yet their influence can be measured. These fleeting entities give rise to phenomena such as the Casimir effect, where two metal plates in a vacuum experience a measurable force due to the pressure of these quantum fluctuations. Virtual particles also help explain the interactions of real particles, mediating forces like electromagnetism. Their constant appearance and disappearance blur the distinction between something and nothing. Space is never a void, but a dynamic arena where existence itself flickers at the smallest possible scales. The universe's apparent stability rests upon this invisible storm of creation that never truly stops. a ceaseless dance of energy beneath the calm surface of reality. Time itself may be quantized at the smallest scales. Just as matter and energy come in discrete units, time itself might also have a smallest possible increment. Some theories of quantum gravity propose that time does not flow continuously, but advances in tiny, indivisible steps called quanta. At scales near the Planck time, around 10 to the negative 44 seconds, the smooth fabric of spacetime may break into fundamental units. If true, this would mean that the universe operates on a kind of cosmic clock with an ultimate resolution limit. Continuous motion and change would be illusions of these incredibly small intervals. Though we cannot yet test this idea experimentally, it offers a path toward uniting relativity and quantum mechanics. The notion that time itself might be granular suggests that even reality's flow is built from distinct moments, woven together into the continuum we perceive. At the Planck scale, spacetime becomes foamy and uncertain. At distances smaller than the Planck length, spacetime ceases to behave smoothly. Quantum effects dominate, turning geometry itself into a frothing sea of fluctuations. This scale, roughly 10 to the negative 35 meters, marks the boundary where gravity and quantum mechanics intertwine. The orderly structure of space and time breaks down, replaced by a chaotic foam of ever-changing connections. Tiny wormholes may open and close, and the distinction between here and there becomes meaningless. Physicists call this realm quantum foam. It represents the foundation of all existence, the place where space-time loses its classical definition. Understanding this regime requires a theory of quantum gravity, which remains one of science's greatest goals. At the Planck scale, the universe's calm surface gives way to a turbulent foundation, a reminder that beneath every structure lies a restless storm of creation. The smallest possible unit of time is the Planck time. Physicists define the Planck time as the smallest meaningful interval that can exist, roughly 10 to the negative 44 seconds. Below this limit, the known laws of physics no longer apply, and the very concept of time loses meaning. It represents the duration it takes light to travel one Planck length, the smallest possible unit of distance. At scales shorter than this, space-time becomes dominated by quantum uncertainty, making measurement impossible. The Planck time marks the ultimate frontier of physics, the edge where our understanding stops. In the earliest moments of the universe, time itself may have operated according to these limits, ticking in discrete steps rather than flowing smoothly. Though unimaginably brief, this unit defines the smallest heartbeat of reality, the quantum pulse from which the continuous rhythm of the cosmos ultimately arises. The Planck length defines the limit of physical meaning. The Planck length, about 10 to the power of negative 35 meters, marks the smallest distance at which the known laws of physics can operate. Below this scale, quantum effects of gravity become so intense that space itself ceases to have a well-defined structure. Attempts to measure or observe anything smaller would require energies so enormous that the region being studied would collapse into a black hole. The Planck length is therefore not just a number, but a boundary that separates the describable from the undefined. It represents the scale where quantum mechanics and general relativity must merge into a single theory of quantum gravity. This tiny distance is unimaginably beyond the reach of any experiment, yet it defines the ultimate resolution of the universe, the smallest pixel of reality, where geometry, energy, and probability are no grade. Longer, separate concepts, but one. Quantum gravity seeks to unite the small with the vast. Quantum mechanics describes the behavior of the smallest particles, while general relativity governs the vast structures of space, time, and gravity. Each theory works beautifully within its own domain, yet they refuse to cooperate at the most extreme boundaries of nature. Quantum gravity is the effort to reconcile them, creating a single framework that explains everything from subatomic particles to galaxies. Near black holes, or at the beginning of the universe, both sets of laws must operate together, but their equations currently contradict each other. Researchers explore many possible paths, including string theory, loop quantum gravity, and emergent spacetime models. Each suggests that geometry and matter are deeply connected, perhaps even interchangeable. Success would reveal the fundamental texture of reality and explain how the universe behaves at its most extreme limits. Quantum gravity is the bridge between the very small and the unimaginably vast. General relativity and quantum mechanics still refuse to agree. Einstein's theory of general relativity treats spacetime as smooth and continuous, while quantum mechanics insists that energy and matter come in discrete probabilistic units. When combined, these views produce contradictions that defy logic. Calculations about the inside of black holes or the earliest moments of the Big Bang yield infinities that cannot exist physically. This conflict defines one of the deepest puzzles in science. Physicists know both theories are accurate within their own scales, but each breaks down when pushed into the other's territory. The cosmos must obey one consistent set of laws, yet we have not found the equation that unites them. Experiments with high-energy particles, gravitational waves, and black hole thermodynamics may offer clues. Resolving this tension would revolutionize physics, revealing a single description of nature that spans from the quantum foam to the structure of galaxies and beyond. Spacetime might be emergent rather than fundamental. Some scientists believe that spacetime itself is not the foundation of reality, but a structure that arises from more basic principles. In this view, space and time are not ingredients of the universe, but consequences of deeper quantum processes. Just as temperature emerges from the motion of countless atoms, space-time could emerge from the relationships between quantum states or particles. If true, the geometry we experience would be a large-scale illusion, formed from an underlying web of information and entanglement. At the smallest scales, there might be no continuous space at all, only discrete interactions that give rise to what we perceive as distance and duration. This concept changes everything about how physics is understood. It suggests that reality is not built upon empty space, but upon the invisible connections that create it, a cosmic fabric woven from the mathematics of relationship itself. Entanglement could be the thread that weaves space-time together. Quantum entanglement is one of the strangest phenomena in physics. When two particles become entangled, they share a link so profound that measuring one instantly affects the other, no matter how far apart they are. Some physicists now think that this connection might form the very fabric of space-time itself. In this picture, space emerges from networks of entangled particles, with geometry representing the strength and pattern of their relationships. The more entangled the system becomes, the more continuous and connected space appears. If the entanglement were broken, space-time might tear apart or collapse entirely. This idea offers a path toward unifying quantum theory and gravity, replacing the concept of space as a background with one where space is born from information. The cosmos may therefore be a vast web of entanglement, each thread holding together the structure of everything that exists. Some theories suggest space is built from quantum information. Modern physics increasingly points to information as the true foundation of reality. In some theories, every point in space corresponds to a tiny unit of data describing the quantum state of the universe. These informational bits interact, exchange energy, and together create what we perceive as geometry and motion. Evidence for this comes from black holes, which appear to store their contents not in volume, but on their surface area. The amount of information they contain scales with that area, implying that space itself might be quantized in similar ways. If the universe is made of information, then physics is a process of computation, and every particle interaction is a kind of calculation. Space would be the structure of that ongoing computation, a holographic lattice of relationships that encodes everything we see, feel, and measure within the vast machinery of the cosmos. Time may flow from the growth of entanglement. Time might not be an independent background in which events unfold, but an emergent property of increasing quantum connection. As systems interact, they become more entangled, forming a web of relationships that grows more complex over time. This rise in entanglement could define the direction of time itself. The universe evolves from simpler states to more correlated ones, giving rise to the arrow of time that points from past to future. In this sense, time is not a fundamental dimension but a reflection of change in the informational structure of the cosmos. As particles exchange information, the fabric of spacetime evolves with them. Clocks measure not a pre-existing flow, but the rate at which systems build correlations. Time becomes the story told by the universe, as it knits together its own structure through entanglement, weaving history from pure quantum connection. The arrow of time points from order to disorder. The flow of time has a clear direction that we experience every moment, yet the laws of physics themselves do not prefer one direction over another. The reason we perceive time as moving forward is because of entropy, the measure of disorder. Entropy always increases in closed systems, meaning the universe evolves from more ordered states to less ordered ones. Broken glass does not reassemble, and heat does not flow from cold to hot without work. The early universe was remarkably ordered, allowing time to have a distinct direction as entropy rose. This gradual increase gives rise to memory, causality, and change. Without it, all events would seem reversible, and the difference between past and future would vanish. Entropy is not merely a statistical property, but the cosmic engine that gives time its one-way current, turning symmetry into history and stillness into motion. Entropy gives time its direction. Entropy describes how many possible arrangements a system can take while maintaining the same overall appearance. As entropy increases, more configurations become possible, and systems drift naturally toward disorder. This process explains why time seems to move forward. To reverse it would require every particle to retrace its path exactly, an event so improbable that it would never occur in practice. The increase of entropy underlies everything from melting ice to the evolution of galaxies. The universe began in a state of exceptionally low entropy, and its steady rise has created the sense of flow and progression we call time. Each irreversible process we observe, from the burning of stars to the beating of a human heart, is a manifestation of this deep rule. Time's arrow is drawn by the mathematics of probability written across every movement of matter and energy. If entropy decreased, time might run backward. If entropy were ever to decrease universally, the distinction between past and future would vanish. Events would unfold in reverse order, with chaos giving way to order and broken systems spontaneously repairing themselves. Physics allows this in principle but not in practice, because it is so statistically unlikely. The number of ways for particles to arrange into disorder far exceeds the number that create structure. A universe with decreasing entropy would erase memory and causality, because causes would follow effects instead of preceding them. Such a reversal challenges our deepest intuitions about time and existence. Although entropy can locally decrease, as in the growth of life or the formation of stars, these processes always produce greater disorder elsewhere. Time's forward motion is therefore sustained by the overall rise of entropy, anchoring every moment in the irreversible unfolding of cosmic history. The early universe was more ordered than today. Immediately after the Big Bang, the universe was smooth, uniform, and dense. Despite its apparent chaos, this was a state of extremely low entropy, meaning it was far more ordered than today's structured cosmos. There were few possible configurations for matter and energy to occupy. Over billions of years, as the universe expanded and cooled, tiny fluctuations grew into stars, galaxies, and planets, greatly increasing entropy. This rise defines the arrow of time. The early simplicity allowed complex structures to emerge as entropy grew, leading to life, evolution, and change. Scientists still do not fully understand why the universe began in such an improbably ordered state. The answer could reveal why time has direction at all. The universe's evolution from smoothness to complexity is not decay, but transformation. A continuous balancing act between order and chaos that drives cosmic history. Every second that passes increases the universe's entropy. Entropy grows steadily throughout the universe, shaping the arrow of time. Every process that converts energy from one form to another contributes to this increase. Stars fuse hydrogen into helium, radiating heat into the cosmos. Black holes consume matter and light, adding to their immense entropy. Living organisms metabolize energy, creating local order while releasing waste heat. Each of these actions marks a small step in the universal rise of disorder. Over billions of years, entropy has increased so much that most of the cosmos is now cold and diffuse, with energy spread thinly across vast distances. Yet this ongoing process also fuels creativity and complexity. The flow of energy from order to disorder allows systems like planets and life to exist briefly in between. Every second that passes deepens entropy's imprint, recording the irreversible rhythm of the universe's unfolding story. Time moves differently near massive objects. Gravity warps not only space, but also the flow of time. Near a massive body, clocks tick more slowly than in regions where gravity is weaker. This phenomenon, called gravitational time dilation, has been confirmed by experiments comparing atomic clocks on Earth and in orbit. The closer a clock is to a planet or star, the more the curvature of space-time stretches time itself. Near a black hole, this effect becomes extreme, with seconds turning into centuries relative to distant observers. The principle is woven into technologies like GPS, which must account for these relativistic differences to function accurately. Time dilation reveals that the universe's rhythm is not absolute but elastic, shaped by gravity's invisible pull. Mass and time are inseparable partners, each influencing the other, creating a cosmos where every heartbeat, every orbit, and every light beam unfolds within curved geometry. Around a black hole, seconds can stretch into eternity. As matter approaches the event horizon of a black hole, the curvature of space-time becomes so intense that time nearly stops from the perspective of a distant observer. To that observer, the falling object appears to freeze in place, fading slowly as its light redshifts into invisibility. Yet for the object itself, time proceeds normally. It crosses the horizon in a finite interval, unaware of how distorted the outside world has become. This paradox illustrates the relativity of time and the power of gravity to bend it. The region near a black hole's horizon is an arena where the geometry of space-time dominates every process, turning seconds into eternities and motion into stillness. What seems eternal from afar is, in another frame, a momentary fall. The boundary between these perspectives defines one of the most beautiful mysteries in all of physics. Near a black hole's edge, light itself struggles to escape. The edge of a black hole, known as the event horizon, marks the ultimate gravitational threshold. At this distance, the pull of gravity exactly equals the speed of light's outward motion. Any closer, and even photons cannot climb away. As light tries to escape from near this region, it loses energy, stretching into longer wavelengths that eventually fade into darkness. This effect, called gravitational redshift, shows that light itself obeys the curvature of spacetime. Observing how radiation bends and slows near black holes allows astronomers to test the predictions of general relativity with extraordinary precision. The struggle of light to emerge from such depths reveals that space and gravity are inseparable. Black holes do not trap light by force alone, but by geometry itself, reshaping the very fabric of the universe so that all paths curve back toward the unseen center. To a distant observer, an object falling in seems to freeze in time. When an object falls toward a black hole, it appears to slow and fade as it nears the event horizon. From far away, the process seems to take forever, as time dilation stretches each moment infinitely. The object's light grows redder and dimmer until it vanishes completely. To the falling object, however, everything feels normal. It crosses the horizon and continues inward without noticing anything special. This difference arises because time and space behave differently for observers in distinct gravitational fields. The black hole's immense curvature causes their perspectives to diverge completely. The frozen image seen from afar is not a trick of vision, but a real manifestation of space-time geometry. It demonstrates that time is relative, shaped by gravity, motion, and position. Near a black hole, even the flow of moments becomes a matter of perspective and distance. To the object itself, it crosses the horizon without noticing. From the viewpoint of an object falling into a black hole, the event horizon is not a wall or barrier, but an ordinary region of space-time. The traveler feels no sudden force or change while crossing it. Locally, physics continues as usual. Yet from an external perspective, the same event looks frozen forever just above the horizon. This paradox illustrates how gravity warps not only space and time, but perception itself. Inside the horizon, all possible paths lead inward toward the singularity, a point where known physics breaks down. For the falling object, the crossing is inevitable and unremarkable, but for an outside observer, it never truly happens. The two perspectives are equally valid within their own frames. This profound contrast reveals that reality and general relativity depends on where you stand and how deeply gravity shapes the passage of your time. Space and time are perceived differently by every observer. Einstein's theory of relativity teaches that space and time are not absolute. Two observers moving at different speeds or located in different gravitational fields will measure different intervals of time and distance between the same events. What one calls simultaneous, another may see as sequential. This relativity of perception arises because space-time itself adjusts to preserve the constant speed of light. Clocks slow down and lengths contract to maintain this universal balance. Everyday life hides these effects, but at high speeds or strong gravity they become profound. This principle reshapes how we understand motion, cause, and even existence. There is no single shared timeline threading through the universe and the countless personal timelines that intersect and diverge. Reality, then, is not fixed from a single viewpoint, but stitched together from the overlapping perspectives of all who move through the geometry of spacetime. Simultaneity is an illusion. Events that seem to happen at the same moment for one observer may occur at different times for another who is moving relative to them. This effect, known as the relativity of simultaneity, follows directly from the constancy of the speed of light. Since light always travels at the same speed, observers moving differently must adjust their measurements of time and space to remain consistent. This means there is no universal now shared across the cosmos. Every observer carries their own slice of reality, defined by motion and position. What appears synchronized in one frame can unfold sequentially in another. This idea challenges the intuition that time is absolute, but has been proven repeatedly through experiment and observation. The universe does not tick in unison but hums in countless overlapping rhythms, each tied to its observer's unique motion through spacetime. Two events that seem synchronized to you might not be to someone else. Imagine standing on a train platform while two flashes of light strike the front and back of a passing train. To you, the flashes seem simultaneous. To a passenger inside, moving relative to the platform, they occur at different times because the motion of the train changes how the light reaches them. Both observations are correct within their own frames of reference. This example captures the essence of relativity, which abolishes the idea of a single universal time. The concept of simultaneity depends on an observer's state of motion, proving that time is woven into space and cannot be separated from it. This relativity of experience does not create contradiction, but harmony. It ensures that all observers agree on physical laws, even if they disagree on when events occur. Time and space adapt perfectly to preserve the unity of the universe's geometry. Moving clocks tick differently than stationary ones. Einstein discovered that time does not flow at a fixed rate for everyone. When an object moves at high speed, its internal clock slows relative to one that remains at rest. This strange effect, known as time dilation, has been confirmed in many ways. Subatomic particles that should decay in a fraction of a second survive much longer when traveling close to light speed. Atomic clocks aboard airplanes or satellites run slightly slower than identical clocks on Earth's surface. None of this is illusion. It is how the universe maintains the consistency of physical laws. Every observer, moving or still, measures the same speed of light, and to make that possible, time itself must adjust. The faster an object moves, the slower its seconds pass. This quiet stretching of time keeps the entire cosmos harmonious, linking motion, light, and experience in a single, elegant geometry. Moving rulers shrink in the direction of motion. Just as time slows for moving objects, space also adjusts. A ruler or spacecraft traveling at high speed will appear shorter along the direction of its motion when measured by someone at rest. This effect, known as length contraction, is a natural partner to time dilation. Both arise because the speed of light is constant for all observers, no matter how they move. To preserve that constancy, space and time must shift together. The object itself experiences no change within its own frame. Everything feels normal. But to an outside observer, distances compress and times stretch, ensuring that the laws of physics never contradict one another. Experiments using high-energy particles have confirmed this repeatedly. As they race through accelerators, their paths and lifetimes behave exactly as relativity predicts. Space and time bend together in perfect coordination, maintaining the balance that underlies the entire universe. Space contracts just as time dilates. Relativity unites space and time into a single structure, and they flex together whenever motion occurs. As an object speeds up, its measure of time slows while its length shortens along its direction of travel. These effects preserve the constancy of light's speed and ensure that physical laws remain identical for all observers. The interplay of stretching time and contracting space reveals that neither quantity exists independently. They are coordinates in a deeper geometry that defines reality itself. For astronauts traveling near the speed of light, the universe ahead would seem compressed, while those remaining on Earth would see the travelers' clocks ticking more slowly. Each observer experiences a consistent world, Yet their measurements differ in ways that precisely mirror one another. The balance between space and time is what keeps the universe coherent, turning relativity from paradox into perfect harmony. Together, they keep the speed of light constant. No experiment has ever found light to travel at any speed other than its universal value in a vacuum. Whether the source moves toward you or away, whether you are running beside it or standing still, the result is always identical. This constancy might seem impossible unless space and time themselves adjust to preserve it. That is exactly what relativity describes. Moving clocks slow, moving distances shorten, and both effects cooperate to ensure that the measured speed of light remains fixed. This consistency allows the equations of nature to hold true for everyone, regardless of motion. It also establishes light as the ultimate messenger of the universe, defining the limits of communication and causality. Every photon travels within a structure that reshapes itself to maintain equilibrium, reminding us that even the simplest constant hides profound unity between distance, duration, and the geometry of telemetry. Reality. Space-time diagrams help visualize this interdependence. To understand how space and time combine, physicists use space-time diagrams. These diagrams plot position on one axis and time on another, turning abstract equations into geometry. Every object follows a world line, a path that shows where and when it exists. A stationary object traces a vertical line upward through time, while a fast-moving one tilts toward the horizontal, revealing how motion blends space and time together. The slope of light's world line defines the speed limit for all motion. Within this picture, time dilation and length contraction appear naturally as simple geometric relationships. The diagram also helps visualize cause and effect, showing which events can influence others and which remain forever disconnected. Space-time diagrams transform relativity into something we can picture, showing that every life, every signal, and every journey is a thread woven through the same four-dimensional tapestry that defines the universe's enda itself. Light cones show which events can influence each other. In the fabric of space-time, every event sends out potential paths for light in all directions. These paths form what physicists call a light cone, the region of space and time that can be reached or affected by that event. The inside of the cone represents everything that can be touched by its influence, while the outside marks what will forever remain unreachable. Light cones define causality, determining which events can affect which others. They grow wider as time progresses, expanding the region of possible influence, but they always remain bounded by the unbreakable limit set by light speed. The geometry of these cones shows why cause must precede effect, and why faster-than-light travel would disrupt reality itself. Every action, from a spark to a supernova, lives within its own cone, shaping the web of connections that give structure and order to the cosmos. Inside your light cone lies everything that can affect you. From the moment of your birth, every photon, sound wave, or particle that has ever touched you has traveled within your light cone. This invisible region defines your personal portion of the universe, containing all events that could possibly influence you and all future events you could someday reach. Everything outside it lies forever beyond your causal contact. The shape of this cone expands with each passing moment, but its boundaries are strict, limited by light's constant speed. Even if you journeyed across galaxies, you could never reach certain distant points in space or times in the future that fall beyond its reach. Your entire life unfolds inside this geometric enclosure. It connects you to everything you have ever seen or felt, while reminding you that most of the universe lies forever beyond the frontier of your possible experience. Outside it lies everything forever beyond reach. The vast majority of the cosmos will remain forever outside your light cone. No matter how long you wait or how far you travel, its signals can never reach you. This limitation arises not from technology but from the fundamental nature of spacetime itself. Light's finite speed defines the maximum extent of influence. Galaxies far enough away recede faster than light due to cosmic expansion, placing them permanently beyond communication. Their light will never arrive, their stories forever unreadable. The geometry of spacetime draws an absolute horizon around every observer, defining a private universe bounded by time and distance. It is a sobering thought that isolation is built into the structure of reality, yet it also gives meaning to connection. Within that reachable region, every ray of light and every shared moment carries immeasurable value, bridging the finite with the infinite through pure geometry. Causality depends on the geometry of spacetime. The rule that cause must precede effect is not merely philosophical, but a consequence of geometry. The structure of spacetime, with its light cones and curvature, enforces a natural order of events. Nothing can travel outside its cone without violating the universal speed limit, so no cause can influence something before it occurs. When spacetime curves around massive objects, these cones tilt and distort, changing the flow of time and the pathways of light. Yet even in the warped regions near black holes, the principle remains intact. This geometric enforcement ensures that reality remains coherent and predictable. Without it, events could occur in inconsistent orders, and the universe would lose its logical structure. Causality is the quiet architecture beneath every experience, sculpted not by human reasoning, but by the fundamental shape of spacetime itself, which preserves consistency throughout the cosmic fabric. Wormholes could bend that geometry in astonishing ways. The equations of general relativity permit solutions in which spacetime folds in on itself, creating tunnels that connect distant regions. These theoretical structures are called wormholes. In essence, a wormhole is a shortcut through the fabric of the universe, allowing a traveler to move between two far-separated points without crossing the space in between. While they have not been observed, their mathematics is sound, suggesting they could exist under the right conditions. Some wormholes would collapse instantly, while others might remain stable if held open by negative energy, a form of matter with unusual gravitational properties. If such structures exist, they could revolutionize our understanding of distance and connection. They show that spacetime is not merely a stage, but a living, flexible entity capable of astonishing configurations that challenge our deepest intuitions about separation and motion across the cosmos. A wormhole links two distant regions of spacetime. Imagine taking a sheet of paper, drawing two dots far apart, and folding it so the dots touch. A wormhole is the spacetime equivalent of that fold, linking distant points in a single continuous structure. In theory, one could enter a wormhole near Earth and emerge near another star or even another galaxy almost instantly. Mathematically, general relativity allows such connections, though keeping them open would require exotic matter with properties not yet observed. Wormholes might exist at microscopic scales, forming and vanishing in the quantum foam of the universe. Others, if large enough, could serve as cosmic bridges. While purely hypothetical for now, their study expands our understanding of relativity, geometry, and energy. Wormholes reveal that space is not rigid but pliable, capable of configurations that merge distant regions into one seamless continuum of cosmic possibility. They are allowed by Einstein's equations in theory. When Einstein's field equations are explored deeply, they reveal solutions that describe wormholes, time loops, and curved pathways connecting remote parts of spacetime. These are not science fiction inventions, but legitimate mathematical results that arise naturally from general relativity. Whether nature actually constructs them is an open question. The conditions required may be extreme, involving gravitational fields so intense and energy densities so exotic that they stretch our current understanding of physics. Yet their mere possibility demonstrates the flexibility of spacetime and the depth of Einstein's insight. By translating gravity into geometry, his equations permit universes far stranger than the one we observe. Wormholes, if they exist, would not break the rules of physics but would instead express them fully, showing that the cosmos is capable of shapes and pathways beyond the limits of ordinary perception. A traversable wormhole might require exotic matter. A wormhole stable enough to pass through would collapse instantly under its own gravity unless something held it open. Theoretical models suggest that this support could come from exotic matter, a substance with negative energy density. Such material would behave in ways completely opposite to ordinary matter, repelling rather than attracting through gravity. Negative energy does appear in certain quantum phenomena, such as the Casimir effect, but only in minute quantities. To hold a wormhole open, one would need enough of it to counteract immense gravitational pressures. Although the idea remains speculative, it demonstrates how relativity and quantum mechanics intersect. The study of exotic matter pushes physicists toward a unified understanding of both realms. If traversable wormholes ever prove real, they will reveal not only new routes through space, but profound connections between gravity, quantum fields, and the deep structure of space-time. Negative energy could hold a wormhole open. Ordinary matter cannot prevent a wormhole from collapsing, but negative energy might. In quantum theory, negative energy occurs in certain situations where the vacuum behaves unusually, such as between two closely spaced metal plates in the Casimir effect. This type of energy exerts a repulsive gravitational influence, the opposite of what we experience in daily life. If enough could be produced and controlled, it might keep the throat of the wormhole stable, allowing safe passage. Although no experiment has achieved this, the concept links quantum mechanics and general relativity in remarkable ways. It shows that the smallest scales of reality could influence the largest, with quantum fluctuations determining the fate of cosmic structures. Whether or not such a feat is ever realized, the idea of negative energy reminds us that space-time remains full of undiscovered possibilities and strange hidden forces. We have never observed one yet. Despite decades of searching, astronomers have found no direct evidence of wormholes. No unusual gravitational signatures, light distortions, or repeating signals indicate that such tunnels exist. That absence, however, does not disprove them. Wormholes, if real, could be rare, unstable, or hidden behind horizons. Detecting one would require immense precision and perhaps new technology capable of identifying their subtle effects on nearby light and matter. Even without proof, scientists study them because they stretch the boundaries of known physics, offering insights into gravity, geometry, and energy. They also serve as valuable thought experiments that help test the limits of Einstein's equations. The mystery endures, fueling imagination and research alike. Whether wormholes remain theoretical or someday become observable, their existence in mathematics shows how deeply the structure of space-time can surprise us with its beauty and complexity. Time travel might be possible through certain wormholes. Some solutions to Einstein's equations suggest that wormholes could connect not just distant points in space, but different moments in time. If one mouth of a wormhole experienced time more slowly than the other, perhaps through motion or gravity, traveling through it might allow a return to the past or a leap into the future. Such possibilities raise profound questions about causality and paradox. Could you visit your earlier self, or change an event that has already happened? Most physicists believe nature would prevent such violations, but the mathematics itself does not forbid them completely. Exploring these ideas helps scientists probe the limits of general relativity and the nature of time itself. Whether practical or not, wormholes remain a theoretical bridge between the familiar flow of time and the deeper, more flexible geometry that underlies the universe. But paradoxes make it complicated. The notion of time travel immediately confronts the problem of contradiction. If you could journey to the past, could you prevent your own existence? Such logical puzzles, known as paradoxes, challenge the consistency of causality. Physicists have proposed many resolutions. Some suggest that the universe forbids paradoxes through a principle of self-consistency, ensuring that any trip to the past simply fulfills history rather than changing it. Others argue that time travel might lead to branching timelines or parallel realities. However, without experimental evidence, these remain ideas rather than realities. The mathematics of general relativity permits closed time-like curves, pathways that loop through time, but quantum mechanics may prevent them from forming. In this tension lies one of physics' greatest mysteries: whether time's flow is absolute, or whether the universe, through its geometry, can bend that flow into strange and self-consistent shapes. Closed time-like curves could allow loops in time. In certain solutions to Einstein's equations, space-time can curl back upon itself, creating what physicists call closed time-like curves. These are paths that return to their own starting points in time, allowing an object to revisit its past. Such configurations arise in theoretical models involving rotating universes or wormholes, though none have been observed in nature. If they existed, they would challenge our understanding of causality and the sequence of events. Yet the equations themselves do not forbid them, showing that relativity allows more flexibility than intuition suggests. Many scientists believe quantum effects or cosmic censorship prevent such loops from forming, preserving order in the universe. Still, the idea fascinates researchers because it reveals how time, under extreme conditions, could behave like a spatial dimension, folding and connecting in ways that blur the boundary between past and future. The universe may protect itself from paradoxes through chronology protection. Stephen Hawking proposed that the laws of physics contain a safeguard called chronology protection, preventing time loops that would lead to paradoxes. In this view, any attempt to create a closed time-like curve would trigger quantum effects that destroy the configuration before it could form. Energy levels might rise to infinity, tearing the space-time apart or sealing the wormhole that would permit backward travel. This principle preserves causality and keeps history consistent. While unproven, chronology protection fits the broader pattern of nature, maintaining coherence even in its most extreme conditions. It suggests that the universe contains built-in defenses against contradictions, ensuring that the sequence of cause and effect remains intact. Time then may be more resilient than it appears, flowing in one direction no matter how deeply we probe the strange geometries that relativity and quantum theory allow. The flow of time could be an illusion of consciousness. Some physicists and philosophers propose that all moments exist at once within a four-dimensional block universe. In that view, the past, present, and future are parts of a single space-time whole, and what we feel as flow is a feature of how minds process change. Relativity supports this picture by denying any universal now. Different observers slice space-time into nows differently, yet the underlying events remain fixed in the geometry. Neuroscience adds a complementary insight. The brain integrates sensory inputs over a small window of a few tenths of a second, building a unified scene that feels continuous. Memory stitches earlier scenes to the current one, and prediction fills in what comes next, creating the sensation of movement and passage. Entropy still provides a physical arrow that orders events, but the sense of flowing from one moment to another may be a construct. In this interpretation, causality is preserved. since causes and effects are embedded in the block, while consciousness paints the experience of becoming. Time may not move at all. Instead, we move through a landscape of moments, and awareness lights one ridge at a time. Some theories say all moments exist simultaneously. In the block universe interpretation of spacetime, the entire history of the cosmos exists at once as a four-dimensional whole. Every moment, from the birth of the universe to its distant future, is embedded within that structure. The passage of time is not something the universe itself experiences, but something perceived by conscious beings, moving through the continuum. This view arises naturally from relativity, which shows that simultaneity is relative. Different observers moving at different speeds disagree on what counts as now, suggesting that past, present, and future are not universally distinct. If this interpretation is correct, the flow of time is an illusion created by perception. All events are fixed within the geometry, like pages in a completed book. What changes is the page we happen to be reading, not the story itself, which is already complete from beginning to end. In that view, time does not pass. We simply move through it. According to this perspective, each instant in time is as real as any other. The sensation of time passing emerges from our consciousness, tracing a path through space-time, like a beam of light sweeping across a landscape. Physics describes the world as a four-dimensional arrangement of events, rather than a sequence that unfolds. We do not watch the future become the present and then the past. Instead, we occupy one position in the continuum after another. Our memories record earlier slices, and our expectations project later ones, creating the illusion of motion through something static. Just as we can move through space, our existence moves through time, revealing new views as it goes. This idea challenges everyday experience, but fits perfectly with relativity's geometry, where change is relative and the universe's structure holds every moment already within it. Space-time could be like a four-dimensional block already complete. Imagine the universe not as something that grows or changes, but as a single, timeless entity containing all events. In this conception, space-time forms a block encompassing every location and every instant. Births, deaths, and cosmic epochs coexist in the same vast structure, each eternally present within its coordinates. The block does not evolve because evolution implies an external time, and none exists beyond space-time itself. What we call the flow of time is our experience of moving along our world line within that fixed geometry. This model explains why physical laws appear deterministic and consistent across all frames of reference. It also dissolves the question of why time moves forward, since the block has no movement at all. Instead, our awareness sweeps through its interior, lighting up one region after another, as though flipping through the frames of an infinite film already shot. The past, present, and future may all coexist. In the most literal interpretation of relativity, all points in time are equally real. The past does not vanish, and the future is not yet to be created. Both exist alongside the present in the four-dimensional structure of the universe. The distinction we make between them arises from entropy and perception. Our memories anchor us to earlier states of lower entropy, giving us the impression of progression. Yet nothing in the equations of physics demands that time must flow from one direction to another. Instead, the unfolding of events is part of a static geometric whole. Every cause, every consequence, and every outcome already occupies its place within space-time's lattice. From our limited viewpoint, we experience the universe as a sequence, but in the broader sense, existence may be a single, timeless sculpture, with every era and possibility carved permanently within it. Your sense of now might be a slice through that block. What we perceive as the present moment could be just a thin cross-section of space-time that our consciousness occupies at any given instant. Imagine cutting a loaf of bread into slices, each representing a single moment. We exist in one slice at a time, with our memories linking previous slices and our anticipation pointing toward those ahead. Physics offers no privileged present. What is now for one observer may be the past or future for another. The sensation of a moving present is generated by the mind, not by space-time itself. Our biology gives us the impression of continuity, but the universe may be static, with every slice already in place. Each observer's world line is a continuous thread through the loaf, intersecting countless other threads, all equally real, all coexisting in the eternal geometry that underlies reality. If so, every event is already written into the fabric of reality. If the universe truly functions as a four-dimensional block, then every event, from the formation of galaxies to your next thought, is encoded within its structure. The future is not yet known to us, but it already exists somewhere along our world line, waiting to be encountered. This interpretation implies determinism at a deep level. The laws of physics fix how the block is shaped, and within that shape, all outcomes are set. Yet this does not mean our choices are meaningless. From within the block, decision-making and causality are genuine processes, even if their results are timelessly defined. What we call free will may be how consciousness experiences its path through predetermined geometry. Reality would then resemble a finished film reel, its frames immutable, while our awareness moves across them, creating the living illusion of spontaneity and change. Yet quantum uncertainty keeps the future mysterious. Quantum mechanics complicates the block universe by introducing probabilities instead of certainties. Before observation, particles exist in superpositions of many possible states, and measurement collapses them into specific outcomes. This indeterminacy suggests that the future might not be entirely fixed. In some interpretations, every possible result exists simultaneously in a larger quantum landscape, and what we experience as the future is one thread among many. Even within a block-like structure, quantum uncertainty could mean that space-time itself includes branching possibilities rather than a single deterministic path. Experiments show that outcomes remain unpredictable, no matter how precisely we measure conditions, hinting that chance is woven into the universe's foundation. Thus, while relativity paints a picture of a completed geometry, quantum theory adds a shimmering layer of openness, ensuring that mystery and freedom remain part of the cosmic design. Observing a system can change its future path. In quantum mechanics, the act of observation does not merely reveal information, it actively shapes what is observed. Particles behave as waves of probability until measured, at which point they assume definite states. This means the future of a system is influenced by how and when we look at it. The famous double-slit experiment demonstrates this principle vividly. When no measurement occurs, particles interfere with themselves like waves, creating patterns of possibility. When observed, the pattern collapses into discrete points, as though the particles knew they were being watched. This phenomenon implies a deep connection between information, measurement, and reality itself. Observers are not separate from the universe, but participants in its unfolding. Each observation alters the configuration of space-time slightly, weaving awareness into the evolution of matter and energy, showing that knowledge and existence are inseparable threads in the cosmic fabric. Measurement links quantum indeterminacy to the flow of time. Quantum measurement transforms uncertainty into definite outcomes, marking the difference between what could happen and what has happened. This transition may be what gives time its direction. Before measurement, the system is described by probabilities that do not distinguish past from future. Once observation occurs, the outcome becomes irreversible, adding a new fact to the history of the universe. This shift from indeterminacy to certainty resembles the increase of entropy, where possibilities collapse into realized events. In this way, each act of measurement creates the sensation of forward motion, with the present serving as the boundary between open potential and fixed record. Some physicists suggest that consciousness might play a role in this process, though others attribute it to purely physical interactions. Either way, measurement serves as the bridge between quantum randomness and the classical order that defines the arrow of time. Spacetime may arise from quantum correlations between particles. Recent theories propose that spacetime itself could be an emergent property built from quantum entanglement. When particles become correlated in certain ways, the pattern of their connections might generate the geometry we perceive as space and time. This idea flips the traditional view of physics. Instead of fields existing within spacetime, spacetime could emerge from the network of quantum relationships themselves. Simulations and mathematical models suggest that the strength of entanglement determines the curvature of the resulting space, mirroring how mass and energy shape geometry in relativity. If true, spacetime would not be fundamental but a large-scale consequence of deeper quantum structure. The distances we measure and the durations we experience would be manifestations of information linking microscopic systems. The universe would then be a vast web of correlations whose structure gives rise to the dimensions that define reality. The universe could be a giant hologram projected from its boundary. The holographic principle suggests that all the information describing the contents of a region of space can be encoded on its outer surface. This means the three-dimensional universe we experience might be a projection of data stored on a two-dimensional boundary. The concept arose from studies of black holes, where the amount of information they contain appears to scale with surface area rather than volume. Extending this insight to the cosmos implies that everything within it, from galaxies to atoms, could emerge from information written on a distant cosmic horizon. Experiments in theoretical physics and quantum gravity support aspects of this view. While we experience depth and distance as real, they might be emergent properties, similar to how a hologram creates the illusion of three-dimensional form from a flat image. The universe may therefore be both tangible and encoded simultaneously. The holographic principle suggests reality has hidden depth. If the universe is holographic, what we perceive as solid, continuous space might conceal an underlying informational structure. Just as a hologram stores a complete image in every fragment, the cosmos may hold its total description on cosmic surfaces. This perspective reconciles gravity and quantum mechanics by limiting how much information can exist within any region of spacetime. Instead of being infinitely divisible, reality contains a finite number of bits proportional to area. Such a framework helps explain black hole entropy and could provide clues about quantum gravity. It also raises profound philosophical questions. If all physical phenomena are manifestations of encoded data, then matter, energy, and geometry might be different expressions of information. The depth we see in the universe would be an emergent effect, suggesting that reality is both more and less than it appears, built from patterns of pure information. Information might be the fundamental substance of the cosmos. In the informational view of physics, everything that exists can be described as data. Particles, fields, and even spacetime itself are seen as manifestations of information processing governed by natural laws. This concept connects quantum theory, thermodynamics, and relativity into a single framework. Energy can be interpreted as the capacity to change information, and entropy measures how much of that information is lost or hidden. Experiments in quantum computing and black hole physics increasingly support this idea. Information cannot be destroyed, only transformed or concealed. implying that the universe preserves its total informational content across all processes. If true, reality is not built from matter, but from relationships and codes, much like a cosmic computation running on the fabric of space-time. Existence itself would then be the ultimate expression of meaning, stored and evolved through universal information flow. Black holes encode their contents on their surfaces, not their volumes. When matter falls into a black hole, its information does not vanish but becomes encoded on the event horizon. This realization solves a puzzle that once threatened the foundations of physics. If information were truly lost, quantum mechanics would be violated. Instead, calculations show that the entropy of a black hole, which measures the amount of information it can contain, is proportional to the area of its surface. Each unit of area holds a tiny bit of information about everything that has crossed the horizon. This discovery linked gravity, thermodynamics, and quantum theory in an unexpected way, suggesting that the three are facets of the same deeper reality. The surface of a black hole acts like a cosmic archive, storing the history of its contents as patterns in space-time, ensuring that the universe's information remains conserved even in the darkest depths. The entropy of a black hole scales with its area, not its mass. Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy depends on the surface area of its event horizon rather than its volume. This means that as a black hole grows, its information capacity increases with the square of its radius, not the cube, as one might expect for ordinary matter. The relationship revealed a profound link between gravity, thermodynamics, and quantum mechanics. It also laid the foundation for the holographic principle, which generalizes this concept to the entire universe. The surface area effectively measures how many bits of information are stored in the black hole's geometry. This result implies that space itself has an informational limit. Only so much data can be encoded within a given area. The insight reshaped our understanding of both black holes and the fundamental nature of reality, suggesting that surfaces hold deeper secrets than volumes. Hawking radiation lets black holes slowly evaporate. In the 1970s, Stephen Hawking showed that black holes are not perfectly black. Quantum effects near the event horizon cause pairs of particles to appear spontaneously. One falls into the hole while the other escapes, carrying away a tiny amount of energy. Over immense timescales, this process allows black holes to lose mass and eventually evaporate completely. The radiation is extremely weak for large black holes, but becomes intense for small ones near the end of their lives. This discovery unified principles of quantum theory, relativity, and thermodynamics in a single, elegant framework. It also raised new puzzles about what happens to the information contained within the black hole. Hawking radiation ensures that even these cosmic abysses participate in the exchange of energy and information, proving that nothing in the universe is entirely isolated from the flow of physics. As they shrink, they leak energy back into spacetime. As black holes radiate, their mass decreases, causing their temperature to rise and the process to accelerate. Eventually, the black hole emits its remaining energy in a final burst of radiation, returning what it borrowed from spacetime. This emission may release subtle traces of the information that once fell inside, preserving quantum consistency. The energy rejoining the universe contributes to its overall balance, ensuring that nothing is truly lost. While the details of this evaporation remain an active area of research, it provides a beautiful symmetry to the cosmic cycle of creation and dissolution. Black holes, once thought to be ultimate traps, become participants in the renewal of energy across space-time. Their slow fading reveals that even the most extreme objects obey universal laws, transforming mass into light and feeding the cosmos with whispers of their hidden histories. The death of a black hole returns information to the universe. When a black hole completes its evaporation, the information it once held must somehow reappear in the emitted radiation to satisfy quantum law. How this happens remains one of the deepest puzzles in physics, known as the information paradox. Many theories propose mechanisms for encoding the lost data in subtle correlations within the Hawking radiation. If true, it would mean that information is never destroyed, only transformed. The process would demonstrate that space-time itself acts as a perfect accountant, preserving every detail of its history. This understanding connects quantum information theory to the large-scale structure of the universe, uniting the smallest and largest realms of physics. The end of a black hole, far from being a vanishing act, may be a final act of revelation, releasing back into the cosmos the story of everything it once consumed. When all black holes evaporate, only space-time will remain. In the far future, after eons beyond imagination, every black hole will have radiated away its mass through Hawking radiation. The galaxies that once contained them will have long faded into darkness, and only faint particles and radiation will persist. What remains will be a vast, thin sea of energy stretching across expanding space-time. In that remote epoch, even the smallest quantum fluctuations will dominate the cosmic landscape. Space-time will continue to stretch, cooling toward absolute zero, until no structured matter endures. The universe will reach a state sometimes called the heat death, where energy is uniformly distributed and change effectively ceases. Yet even in this final silence, space-time itself will endure for a while longer, holding the last remnants of information, the quiet echo of creation, before it too may dissolve into something beyond physics as we call know it. Space-time might one day fade too, leaving pure quantum nothingness. Some cosmological models predict that space-time itself is not eternal. If it emerges from quantum processes, it may also dissolve when those processes end. In the universe's final moments, fluctuations could fade, and the very fabric of space and time might disintegrate into a state with no geometry, no duration, and no distance. This quantum nothingness would not be empty in the ordinary sense, but a primordial potential, the same kind that once gave birth to the cosmos. From it, new universes might arise, each with its own laws and dimensions. In this vision, existence is cyclical, with space-time emerging, evolving, and dissolving endlessly. What appears to be the end could be a return to the source, where reality rests between manifestations, waiting for another spark to ignite the vast unfolding pattern of being once more. You have reached the end of our journey tonight, a quiet voyage through the deep geometry of reality itself. Together we have followed the thread that binds space and time, watching it curve under the weight of stars, ripple with the dance of black holes, and stretch with the breath of the expanding universe. Every motion, every flicker of light, every passing second is shaped by that same invisible fabric. It holds everything in its gentle structure, from the smallest particle to the largest galaxy. Now let your thoughts slow to match the calm rhythm of the cosmos. Picture the faint glow of starlight crossing endless distances, the hush between galaxies, the soft pulse of time flowing onward. You are part of that same harmony, resting within a universe that is vast, ancient, and alive. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, and let the universe cradle you in its quiet curve, still, timeless, and free. Sleep well and good night.